Thanks, everybody, for being here and giving me the chance to talk to you about this stuff. Switched orders today because I'm going to be talking to you about putting the results in context. We have these rotation samples that are available to us now. We have this 300-star sample that has measured asteroseismic ages and rotation periods. And it's begging to be used as a gyrochronology calibrator. And we have this 34,000-star sample, among others, where you would really like to use gyrochronology to tell you the distribution of ages of stars that you see in this thing. But what I'm going to talk to you about today is how you have to be careful about how you do that. You have to care about the populations. You have to realize that not all stars have gyrochronology relationships, and basically take you through some of the selection effects and caveats that you need to be aware of. So Savita showed you this plot already. This is this Skumanich paper from 1972. Where he showed that there's a relationship between the rotational velocity of stars and their age, that it declines as 1 over the square root of the age. This is the basis for gyrochronology, the idea that you can measure a rotation period and an age in systems where you can get independent calibrators, and then given a period for a random field star, you're able to determine an age. And this is hard to do in other ways for a random field star. So we've been doing gyrochronology from the ground. What basically has been done up until this point is you go out, you look at open clusters where it's easy to get an independent age, relatively, and you measure rotation period as a function of mass, and you calibrate this empirical relationship that its inputs are the stellar color, because there is some dependence on mass, and a rotation period, and out of this relationship comes an age. Now, the problem with doing this from the ground is that you're limited as to the objects that you can look at. Most of the open clusters that have been used for these kinds of studies have been a giga-year-old or less. And actually, rotational evolution is complicated when you start looking at young stars. You really would not like to do it there anyway. But these are the clusters that we had. So you have the young clusters here. For a long time, basically the only calibrating point we have at ages similar to the sun is the sun itself. You have no information about rotation periods as a function of mass, largely at the solar age. You don't have much information about stars older than the sun, and you have almost no information about the way that rotation depends on metallicity. So the obvious thing you would like to do is to fill in this part of this diagram with some independent age calibrators, which is exactly what asteroseismology promises to give us. So this is that 300-star sample with ages from the Chaplin et al. Paper and rotation periods from the work that Savita presented. And what I've overplotted on this diagram are the curves predicted from an empirical gyrochronology relationship that exists in the literature. This is the Mamajek and Hillenbrand 2008 curves. And it's for a range of masses. It's for, I think, 0.8 to 1.2 solar masses. This is the regime over which the relationships are calibrated. And so if your object is following the gyrochronology relationships as they appear in the literature, you'd expect them to fall, your stars to fall somewhere between these two curves. Exactly where they fall will depend on their mass. And what you see is if you look at this and you just take this at face value, it doesn't look very much like this relationship is describing the data. If you were to just fit this with some kind of relationship, you'd get a much shallower period-age relationship. But in fact, the picture is more complicated. We have theoretical expectations about how stars should rotate as a function of their location on the HR diagram. And we have kind of 3 regimes that we can think of. We have cool dwarfs. These are the things that have a relationship between period and age. They have deep convective envelopes. They have magnetic braking, so they can lose angular momentum as a function of time. So these things are the targets you would like to have for gyrochronology. We also have the hot stars. These things are above what we call the Kraft break, which is located here. It's an empirically known thing that cool stars are slow rotators and hot stars are rapid rotators. And we think this is because the convection zones of these hot stars are very thin. They don't undergo magnetic braking. You have no magnetic field that you're driving, and so you're born rapidly rotating, just as the cool stars, but the cool stars spin down and the hot stars don't. And then you have the subgiants. This is a mixture of things that were born above and below the Kraft break, and now you have 2 things that matter. You have ongoing magnetic braking for the stars that started off as dwarfs here. For the hot stars, you now all of a sudden have developed a deep convective envelope as you move across the subgiant branch, and so you begin to spin down because your braking should turn on. We think there hasn't been a lot of data in this region. And you also have the physical expansion of the star that ends up mattering. These things are expanding a lot as they move across the subgiant branch. And so these 2 physical effects give you a relationship between period and age, but it's different than that exists on the main sequence that has not yet been calibrated in the literature. So when you think of gyrochronology, it's only these stars here that are valid targets. So we have this diagram again, and because this is a very well-studied sample, we can actually break it up into the regimes that I talked about. Where the hot stars are in purple, the dwarfs that should have a gyrochronology relationship are in red, and the subgiants are in yellow. And you can see now, if you look at the dwarfs, that they tend in general to fall between these two curves. And it looks much more reasonable that this relationship might be describing the rotation rates of these stars. Hot stars have no relationship between period and age. They're not spinning down. Subgiants show up at periods that are far too long given their age, if you think gyrochronology relationships should predict that the relationship between period and age should be given by these relationships. You also see that there's a lot of overlap. If you don't know what you're looking at, you could be very confused, as these stars all tend to live for some period regimes in the same spot, so you have to be careful. Now, let's suppose for a moment that we can do this calibration. We're able to separate which stars we can target for gyrochronology and which stars we can't. We can come up with a period-age relationship. This is, I think, the 4th time you've seen this diagram today. This is the 34,000 star sample. Overplotted on this are isochrones, gyrochronological isochrones, various literature calibrations. And you can see that there are a lot of features on this diagram, some of which Svi talked to you about, and some of which I'm going to point out in more detail now. There's this sharp cutoff, which appears to fall at the 4.5 gigayear gyrochronological isochrone. And then you've got the locus of points here, some rapidly rotating things at all effective temperatures, and some spray of points that show up at long periods as well. So being theoretically inclined, my reaction to this particular data set was to say, well, let me see if I can reproduce this based on my models. So what I did is I took a galaxy model of the Kepler field, which gives me a distribution of masses, of ages, and metallicities. And then I have models that predict rotation period as a function of all of these things. And so I asked, what would I see if I just produced a magnitude-limited sample that had the same effective temperature cuts, log G cuts, and magnitude limit as this sample did? You get something that looks like this. You have many periods that are far longer than the ones that you're seeing in the actual data. You have spray of points up here. You've got some group of young things that are showing up very rapidly rotating, although the models can't really be trusted down here, so you should take these with a little bit of a grain of salt. But because this is a model, I know what these things are, and you can color code them. And you can see that there's a lot of overlap between these different regimes. It's only the red main sequence dwarfs here that are the things that you can do gyrochronology on. And if you were to live in this regime of the part of the diagram, you could see that there's substantial overlap, and you might pick out a given star, which any given star in this large sample doesn't have necessarily excellent information, and you could get the relationship wrong. Now, this is not the only thing that we can imagine doing to this group of stars. We know that there's a relationship between the amplitude of variability that you'll see from spot modulation in a star and the Rossby number. The Rossby number is the rotation period divided by the convective overturn timescale. And it goes in the sense that the closer the Rossby number is to 1, the more active and variable the star is. And as you move to larger Rossby numbers, the star becomes very, very quiet. And so you can imagine making a Rossby number cut. And to make this cut, I've assumed an empirical relationship between Rossby number and amplitude that's calibrated on an open cluster. I've made a cut that makes sense based on the kind of limits that were seen in this McQuillan paper, the 34,000 stars. And when you do that cut, you get something that looks like this. So what it's done now is it's given you this sharp edge that you're seeing in the data. You've lost a lot of your hot stars because their amplitudes of variability are small. You've lost a lot of your slow rotators for the same reason. You have this spray of subgiants that survives this cut because at fixed effective temperature, the convection zones of these guys are deeper than those of the main sequence counterparts, and so they can survive at a similar Rossby regime at longer rotation periods. And so that's why you see them and not the main sequence stars. And what happens now, I forgot what I was going to, okay. So what you'd want to do then is say, what happens if I look at just the dwarfs, if I look at only the red things, and I say, what's the difference between the dwarfs in this sample and the dwarfs with a Rossby cut? You can plot up the age distribution of objects in those two samples, and what you get is this. In the raw sample that doesn't have this amplitude, this detectability cut, you see that you will detect things all the way out to 10 gigayears. But as soon as you start saying, I can't detect things below a certain threshold, all of a sudden you're only able to see things that are 5 gigayears old or younger. And it has nothing to do necessarily with the fact that those objects don't exist in the field. It just has to do with the fact that you can't detect them. They're invisible to you as far as you're concerned. And so this edge here could very well be due to a detection limit, or it could be telling you something real about the population of the stars in the field. But you have to be careful when you interpret it, because it could be either or. You notice there are a fair number of points living up here. And one of the other things that we can imagine doing is asking what happens if you were to consider blending. The Kepler pixels are fairly large. It's easy to get stars blended together in these pixels. And you would like to hope that the rotation period that you measure for a particular star is the rotation period attached to that star. But it very well could be that you're seeing a 6,000 degree star blended with some kind of M dwarfy thing whose amplitude of variability is just so high that you detect the rotation period of the M dwarf at the temperature, effectively, of the hot star. And so this is just an analysis where I draw from the actual sample, which are the black ones here, draw a companion, ask which star would be detected at what amplitude, which period would you have detected when you blend these two sources, and at what effective temperature. And you can see that you end up getting some points up here. You have the subgiants that are there and real, but you also have some points that are hot stars that are blended with cooler stars, and so they show up in this part of the diagram. And so you need to be careful when you're interpreting rotation periods that are based on potentially blended data. Another thing to note is that there are many blends that show up in regions that you wouldn't necessarily tag them as odd stars. Things sticking up out here might be worrisome because they look different than the others, but you might not necessarily think that any star you detect in here is necessarily a blend, but you need to be careful that it could be. So basically the conclusions here is that if you want to use gyrochronology, you may be very limited based on the kind of sample that you have as to the ages that you can detect. And one of the unfortunate things is that even with tests in Plato, we're not talking orders of magnitude improvement at all in the photometric precision. We're not talking longer time series, and in fact, many cases we're talking much shorter time series. And so if we can't detect it here, if this is actually what's going on, we might need to think about the fact that gyrochronology may only work out to about 5 gigayears, if this is actually what it is. When we go and calibrate the gyrochronological relationships, we need to make sure that we draw the calibrators carefully. We need to make sure that we're not calibrating on hot stars or stars that are evolved, so that we have a relationship that's valid in these regions. And so I think I'll leave it at that and take any questions.
Great. So I see a lot of hands raised in the audience, and luckily I think we might have time to take all the questions. Let's start with George.
Yeah, Jennifer, the question is, for your idea of blending, do you see any sort of dependence on galactic latitude within the Kepler field? That might be a way where you could tell whether that's a factor or not.
Yeah, so this here is just a really crude analysis of what would a blended population even look like. This is the simplest thing you could imagine doing that I did just to see if you could recover some of them. And I definitely am going to do a much more careful analysis of ways that you can pick it out and particular regions that are subject to this kind of thing. But it's just to give you a general idea of how it might affect your sample.
Okay, we have a question right at the back.
Jennifer, this is beautiful work. I didn't hear you use the word binarity, and I'm wondering if that's because it's not going to influence things very much, or it's just a can of worms you didn't want to open?
No, it's a can of worms. So it's fairly likely that a lot of this array of points down here could be due to binaries. This is very rapid rotation. Binarity can affect you in many ways. It can either spin you up. If you're kind of a low mass star, it will spin you up. If you're more of an A star, it can actually spin you down, depending on what spectral type you are. And so it's going to be complicated, and it's another thing. It's in the regime of blending where it might be very difficult to tell that you're affected by binaries. It's definitely a can of worms.
I know there are people spectroscopically following up some of these more rapid rotators to find out if they're binaries. Okay, Victor?
Jen, well, this is beautiful work, really. Just a comment, a word of caution. When picking up the calibrators, you show the Chaplin sample and the ages there. Just a reminder for everyone, actually, that when we did those ages, we did not have metallicity. So we assumed the bulk metallicity of the Kepler field. So if you're using those ages for now, please, grain of salt, or actually bulk of salt.
And there was one question from Tristan in the white shirt.
Yeah, you mentioned about the theoretical model behind parameterizing with the Rossby number. There's two parameterization. I guess one is on the amplitude that you can see, so where you can have the cutoff, and then there's the other one for the what you call the Kraft transition. And I was wondering what you used for that.
So the cutoff comes from this. This is from a paper by Hartman where he looked at M37. The amplitudes that you're seeing in this cluster are much larger than the amplitudes you're seeing in the Kepler sample because this is a ground-based survey. The reason I chose this over the amplitudes in the McQuillan paper is because this is a cluster where we think we know the masses and we think we can calculate the Rossby number for these things. So it's obviously not ideal, and I would definitely like to do a more careful job of making sure that whatever the amplitude cut is, it's more, or however you do this relationship, it's a reasonable one. The idea was just to show what would happen if you had something that was a reasonable assumption. How does it affect your sample? And I think the other part of it was how do you deal with the Kraft break? That is included, there's a convective overturn timescale scaling that's included in the breaking law, so that once your convective envelope gets very, very thin, it very naturally reproduces the Kraft break in a particular breaking law that these models use. It's a paper that Mark Pinsino is working on. It's nearly submitted. But it's similar to the kind of koala laws, and it's nothing very, very different from the general body of literature that's out there, but it does have this convective overturn timescale scaling that allows it to gracefully handle the transition to these hot stars.
Hi, can I put you on the spot?
Sure.
Would you say that we could use gyrochronology as a tool?
So this is the way I view gyrochronology right now. It has a very limited regime, and it keeps getting eaten away the more we learn about it. So doesn't work for the hot stars because they don't spin down, so they're out. The cool stars, the very low mass stars, everything's born with a range of initial conditions, and the spin down is a function of time. These things retain initial conditions for a long time, so they become not very great. They don't have a very great period-age relationship, so the very low mass stars are out. Very young stars are out because these things have disk locking, they have core envelope decoupling, they have sensitivity to initial conditions. So things at younger than half gigayear are out. And now if this is the case that either something funny happens at very, very high Rossby numbers or you can't detect these things, things above 4 gigayears are out. So it sounds gloomy, and I hope it's not the case, but these are the kind of boundaries in which we have to operate. And I think it's important to understand that these boundaries exist. And we should be very aware when we try to use these kind of calibrations that this might be a problem for us.
I guess we should thank Jen again.